Welcome to the fifth video in a series designed to provide guidance in the process of setting up and running a sediment transport model with SRH2D. In this video, we will cover the special topics of model sensitivity analysis and troubleshooting. Lessons will include suggestions for how to test the sensitivity of a model to the input sediment load and the time step, and suggestions for addressing model failures with a time step warning message. Once a sediment model has been built and is capable of running the scenarios necessary for the analysis task, it is important to develop a sense of how much the model results are influenced by user-controlled parameters. Such work is called sensitivity analysis because the goal is to develop an understanding of how sensitive or insensitive a model is to the given parameters and may help inform what additional model revisions may be helpful. Particularly with sediment modeling, where data is frequently limited and parameters are commonly based on general assumptions, the results of sensitivity analyses can help provide confidence in the analysis conclusions. In sediment modeling, it is common that the actual upstream sediment load is not well understood or characterized. While the capacity feature in SRH2D provides a convenient estimate for the sediment load based on the local hydraulics and bed material, it should be understood that the actual load present in the modeled system may be higher or lower than the theoretical capacity due to additional factors outside the modeled area, like upstream disturbances or seasonal fluctuations. With this in mind, the modeler is encouraged to develop a set of model runs with sediment loads higher and lower than the initial base run and explore the result sets. To do this, the first step is to capture the sediment load of the base run. This model is executed with the capacity feature enabled for the sediment inflow. During a model run, SRH2D reports the calculated capacity along with a number of other output files in a subdirectory of the model project. So for the first part of the task, we must find and open the appropriate output file. From the location of the model project, navigate to the folder with the same name as the model project. Then to the SRH2D folder, then to the folder with the name of the base simulation. Then finally to the Output Miscellaneous folder. Within this folder, all of the file names start with the case name assigned by the user, or just the word case if left unchanged, as was done for this model. The file that records the calculated incoming sediment load at the upstream boundary has the case name followed by the characters ln, then underscore, then inlet q1.dat. This file records the calculated incoming sediment load at the upstream boundary. Open this file in any text editor and the user can see this file reports the simulation time and the volumetric flow rate of solid sediment in each of the declared size classes. The last two columns are the water discharge that drives the capacity calculation and the water discharge crossing the inlet boundary. In this example, the model was set to run for 5 hours in hydraulics only mode, so while initially a flow of 1,000 CFS crosses the inlet, no sediment calculations are made until the 5-hour mark. After that mark, calculated values appear in each column for the duration of the model run, in this case, 400 hours. The user can see that the flow rates for each size class change slightly between time steps, which reflects small changes in the hydraulics at the boundary. Under a constant discharge, in most cases these values will quickly approach a value that is effectively constant. The modeler can use information from this output file to create input sediment files of both a higher and lower amount. One way to do so is to capture the header from this file and paste it into a new text file. Then capture time and flow rate data from the file. In this case, the last line of data was captured as representing the constant equilibrium flow rate. Pasting that data in the new text file provides the structure for creating a new time series sediment input file. The format for a time series sediment input file is time in the first column, then flow rate of each size class. There is no need for additional columns of water discharge, and so are deleted, though they would be ignored by SRH2D if not removed. For this study, we want to see the effects of increasing the sediment load by a factor of 5. A convenient way to do this is to copy the flow rate into a spreadsheet program multiply each value by 5, and then paste the new values into the input file. A time series input file should start at time 0. SRH2D recognizes both tabs and spaces as delimiters between columns, and formatting can help the user more easily read the file. We want to keep the sediment load constant for the entire 400-hour run, so the row can be copied and that time column updated to 400 hours. It is good practice to add meaningful comments in the header rows and then save the file with a meaningful name. To use this input file, duplicate the boundary condition that uses the capacity calculation. Be sure to give this new coverage a meaningful name. Double-click on the arc for the input boundary condition to open the boundary condition assignment window, and change the input source to the created file. Then, duplicate the base simulation, ensuring to give the new simulation a meaningful name, and replace the base boundary condition coverage with the increased sediment load coverage. Save and run the simulation, and load the results when complete. Using a similar process, an input load file with the capacity load divided by 5, or 20% of the capacity load, can be created. Use the spreadsheet to multiply the capacity load by 0.2. Copy and paste the new values into the text file, replacing the existing values. Be sure to update the comment lines, and saving with a new name that reflects the input load. Then create a new boundary coverage and attach the input load file to the appropriate arc. Then create a new simulation with a meaningful name. Removing the old boundary condition and attaching the new one. Save and run the simulation, and load the results when complete. The goal of this sensitivity analysis is to assess what effect varying sediment loads will have on our area of interest. One way to do that is to look at how this influences the flow of sediment across a monitor line within the model. This model was executed with a number of monitor lines. Note the displayed arc ID for each line. In addition to the output at each model element displayed in SMS, SRH2D writes additional output for each monitor line. An examination of this output can provide additional insight into the model performance. To view the monitor line output, navigate to the same miscellaneous output directory as was done previously. Monitor line output is recorded in the files that start with the case name, followed by _LN, and then the monitor line ID number. For this analysis, we will examine the results from monitor line 6, which is approximately 700 feet upstream of the area of interest. Opening this file in a text editor reveals output results with simulation time, volumetric water flow across the line, volumetric flow of total solid sediment across the line, total concentration across the line, average water surface elevation at the line, average bed elevation of the line, minimum bed elevation of the line, and then the volumetric flow rate for each sediment size class across the line. Copying the results into a spreadsheet program and plotting the total sediment flow with time provides insight into the behavior of the model over time. In this case, the first 5 hours have no sediment calculations, followed by a large spike of sediment flow that decreases over time as the model adjusts to the flow and sediment combination. These results can be compared to the simulation with 5 times the sediment input by navigating to the same output directory for that simulation, capturing the data for the same monitor line, and plotting against the base simulation. And similarly, capturing the comparable data from the simulation with 20% of the sediment input and plotting the results presents the bracketed effects of an increased or decreased sediment supply. In this case, these results show that over a sediment input range of plus or minus 500%, the response of the model just upstream of the area of interest varies by only about 20%. This is an encouraging response and suggests the analysis of the area of interest may not be heavily influenced by uncertainty in the sediment load. Reviewing the results of different monitor lines from the same simulation can provide additional insight into the behavior of the model run. To illustrate this, we will create a plot of 2 monitor lines from the base simulation. First, we will copy the spreadsheet and turn off the plot of the 20% sediment load results so that only 2 plots remain. Then we will turn back to SMS workspace, capture the results from the base simulation at monitor line 3. Monitor line 3 is located approximately 500 feet downstream of the bridge opening. Opening the output file and copying the contents of the file allows us to paste the results into the duplicated spreadsheet. Be sure to update the field with the proper legend title. This comparison shows that the spike in sediment transport across line 3 once sediment calculations began after 5 hours is smaller than upstream across line 6. What is most noteworthy is that during the first part of the sediment run, more sediment crosses the upstream line 6 than the downstream line 3, implying that the bridge area between the lines is net depositional. Then, after about 200 simulation hours, the behavior flips and more sediment crosses the downstream line 3 than line 6, indicating the area between is erosional. This is likely the effect of the channel adjusting from the initial bed conditions that reflect a topographic survey at a point in time and the bed condition that would evolve under the model flow condition. In this case, a moderate flow level of 1,000 CFS that was sustained for about 16 days. This exercise was performed with the raw output files and external software. If you choose to use SMS, you may be able to access this kind of information within the software. Future users can check for additional features available by right-clicking on the simulation, selecting Tools, and then View Simulation Plots. This example demonstrates that monitor line analysis can provide useful insight into the general behavior of a developed model. And while it can't tell the entire story, it may be considered one part of a complete analysis of a system. And it is ultimately up to the modeler to exercise judgment in determining its appropriate value for the analysis task at hand. It should be noted that this behavior reflects a single flow condition, and the relevance and significance of this insight will depend on the full context of the analysis task at hand. The illustrated example of comparing sediment flow across monitor lines is intended to provide an introduction to a type of analysis that is common in sediment transport modeling, and it is ultimately up to the modeler to exercise judgment in determining its appropriate value. It may also be helpful to check the sensitivity of results to time steps. You will want to confirm that a smaller time step does not produce meaningfully different results, and establishing that a longer time step is valid can help if the analysis will require multiple runs or a very long hydrograph. Referring back to the base model, we can confirm that it was run with a 3-second time step. In this exercise, we will create duplicate models with 5-second and 1-second time steps and compare the results to the base model. First, we will duplicate the model, open the model control window, and change the time step to 5 seconds. Then give the simulation a meaningful name and save and run the simulation. And load the results when complete. Then we can create an additional duplicate model, open the model control window, and change the time step to 1 second. And as before, give the simulation a meaningful name, save and run the simulation, and load the results when complete. One way to examine the effect of different time steps is to identify differences in the model topography throughout each simulation. As mentioned in a previous video, the erosion deposition output variable reflects changes from the original topography, with positive values indicating erosion and negative values indicating deposition. Setting up a display scheme to clearly illustrate the positive and negative values can be helpful when reviewing the entire model extent. One way to do that is to open the Display Options window and select the Contour tabs from the 2D Mesh option. On this window, you can see the range of values for the variable and set an appropriate range that centers on 0. For a contour interval, select the Number option and enter an odd number value. In this case, we'll enter 7. Next, change the contour method to Color Fill and specify each color. When reviewing changes in topography, it is helpful to identify a range that, although is not absolute 0, represents no effective change. In this case, we will assign the middle band of colors white and then choose specified values for the contour interval. This allows us to set a range between negative 0.1 feet and positive 0.1 feet as the range where topographic changes are insignificant. These areas will be colored white. Setting the remaining values to -1 and +1, respectively, sets the shading and intensity of the warm and cool colors. Then click OK. This scheme allows the user to clearly identify areas of erosion, deposition, and insignificant bed change. This is just one potential way to view such results. Be sure to check future development of SMS display options and themes for additional approaches. Selecting the erosion deposition variable for each of the 3 simulations indicates results that are quite similar, and it is not easy to identify where any differences may occur. To examine the differences in more detail, we will use the Dataset toolbox. Select the Dataset toolbox from the Data tab on the main menu and ensure Compare Datasets is highlighted. This feature will compare datasets at every output time step between simulations, and this exercise will compare bed elevations. Select the bed elevation output for the base simulation with the 3-second time step. Then select the same output from the simulation with the 5-second time step in the alternative pane. We will call the computed dataset base minus 5 second as a reminder of how the results were calculated. Then click the Compute button and see that the dataset has been added to the Project Explorer. Then select the bed elevation output for the simulation with the 1-second time step in the alternative pane and change the dataset name appropriately, and click the Compute button to create a second computed dataset. Clicking the Done button closes the Dataset Toolbox window and highlights the base -1 second dataset. The dataset is mostly white, indicating topographic differences between the simulations are less than 0.1 feet. For reference, selecting the erosion deposition result from the base simulation shows significant topographic changes in the bed. To examine the base -1 second data set in more detail, we will select this layer and zoom into the area around the bridge, which is our area of interest, and see that some differences do exist in the channel, both upstream and downstream of the bridge opening. In this display, cool colors indicate the bed elevation for the base simulation are higher than the 1 second simulation, and the opposite for warm colors. Selecting an output location colored blue shows that the magnitude of the difference at this location is approximately 0.6 feet. Then switching to the erosion deposition layer on the base simulation shows that at this location, after 400 hours, the model predicts 1.6 feet of erosion. With the interpretation that the base simulation is 0.6 feet higher than the 1 second simulation, this means the 1 second simulation predicted a total of 2.2 feet of erosion. The full significance of this difference at this location depends on the analysis task. It can be noted that differences between the two simulations appear isolated and limited in extent, suggesting that for the modeled condition, decreasing the time step from 3 seconds to 1 second may not necessarily improve the analysis. Reviewing the full extent of base -5 second comparison dataset shows a similar level of differences. Zooming into the area of interest shows small scattered areas of negative and positive differences. Selecting a location with a relatively large difference shows the base simulation predicted a bed elevation that is approximately negative 0.8 feet lower than the 5 second simulation. Checking the results from the base simulation shows that a total of about 8.3 feet of erosion is predicted after 400 hours, which helps put the 0.8 feet of difference between the base and 5 second simulation in context and helps inform whether or not increasing the time step to 5 seconds, thereby shortening the runtime, is valuable for the analysis task. This process of comparing computed datasets is one way that a modeler can evaluate the impact of the time step on a sediment model simulation. And it is up to the judgment of the modeler to determine the significance of this impact on the analysis task at hand. Experienced users may be familiar with a runtime error where SRH2D reports trouble with calculations and suggests reducing the time step as a solution. While this may be helpful in some circumstances, sometimes the solution is improving the quality of the model mesh. In this example, a sediment model was created and failed after 16 hours of simulated runtime. The message generated by SRH2D suggests further reduction of the time step would help the convergence. This result is unexpected because the flow conditions are not particularly extreme. Repeated attempts to reduce the time step from 5 seconds to 1 second to 1/10 of a second confirmed the suspicion that the issue is not inherently with the time step. In this case, it can be helpful to examine the mesh and see if improvements can help resolve the issue. This model mesh includes an area with an abrupt transition from larger elements to small elements through a bridge opening, and then back to larger elements. Turning on the mesh quality feature for this mesh display reveals a high concentration of area change violations. This means that the area of one element is more than twice that of an adjacent element and may lead to computational problems. This is not an uncommon result of transitioning from large to small elements and vice versa. It is not always necessary to address all area change violations in a mesh, but a high concentration of similar violations is something to avoid. In this situation, the abrupt transition of rectangular elements was smoothed to a more gradual transition up and downstream of the bridge opening. The density of triangular elements in the floodplain was increased to address a similar issue. With these changes in place, The model was now able to run to completion with the original 5-second time step. This concludes the video on sensitivity analysis and time-step troubleshooting. In this video, we discussed the value of testing the sensitivity of a model to varying input sediment loads and how to view and compare monitor line data. We also discussed reasons for testing the sensitivity of a model to smaller and larger time steps by comparing output datasets. And finally, we showed an example where a fatal error with a time step warning was corrected by improving the mesh quality. In the next video, we will discuss cohesive sediment modeling. For more information on additional videos, documents, and other reference material about two-dimensional modeling in SMS, please navigate to the link provided here.